Okay, let's solve an example problem of hydrostatic forces on a curved surface. Here we have this 4-meter width quarter circular gate. Its radius is 3 meters. It has a negligible weight. It's hinged at A, and there's this spring here where we want to find the spring force that holds that gate together. So the first approach that we could take is to define some volume of the fluid that's inside that gate between A and B. Knowing the pressure on the vertical projection, we could find out what that force is, and on the horizontal projection, we could find that force. Then we'd find out the force that is exerted on the gate from the fluid, or equal but opposite the force the fluid exerts on the gate. We're not going to do this approach because that adds an extra step in the middle, because then we'd need to go and later do a free body diagram on the gate itself, looking at the reaction forces in the springs and the force from the fluid. So instead we'll do this approach where we include the fluid and the gate together as one system. So here's that system here. We still have that horizontal force and that vertical force from the pressure of the fluid acting on these projections. Now we have the force of the spring. We have the reaction forces at that hinge. And we have the weight of the fluid inside the system that we're defining. So we know that the pressure is, or the force from the pressure is equal to the area multiplied by the pressure at the center of gravity on that vertical plane and the horizontal plane. Now on that vertical plane, the force acts at the center of the pressure, which is at some distance from the center of gravity. So we can represent these pressures now as Fx and Fy, forces exerted on that vertical and horizontal surface. So let's start off finding this Fx here. So it's the pressure at that center of gravity multiplied by the area, or the density multiplied by gravity multiplied by the height at that center of gravity multiplied by area. So we have the density of water is 1,000, gravity is 9.81. And now that height is half of that 3-meter radius. So this height here is that radius divided by 2, or 1.5 meters. So I'll put that in the equation. And now we have our width is 4, and that height is 3. So we have 12 meters squared for the area. And we get 176.6 kilonewtons for that force Fx. Now, if we want to know where this force is applied, we need to know this position of the center of pressure relative to the center of gravity. When we have a formula for that, it's called YCP, and we have this second moment, the second moment of inertia in here. I'll substitute the values in there. We have a 4 meters and 3 meter height. Cubed divided by 12, that's 9 meters to the fourth. So I'll sub that back in the equation here. This thing's at a vertical, so that's 90 degrees. The center of gravity is 1.5 meters from the surface. Our area is 12 square meters. So that's negative 0.5, or 5 meters below the center of gravity. So let's draw this diagram in here. Again, let's do this quite quickly. We have our weight, we have our Fy, we have our Fx here. Actually, let's draw that Fx closer to where it'll actually be. So we have our center of gravity, that's 1.5 meters, and now our center of pressures, another half meter below that. So let's go and calculate what that force Fy is now. We have rho GH, where that H is at the center of gravity of that horizontal surface. So we'll sub in numbers: 1,000 for density, 9.81 for gravity. It's 3 meters below the surface, and we have a 12 square meter area. So if we calculate this out, we get 353.2 kilonewtons. All right, let's start on a fresh page, but let's bring our diagram forward. So here's our system again with our spring and our reaction forces. We've calculated Fy from the pressure of the fluid below. We've calculated Fx from the pressure of the fluid to the left. That was 176.6. We have some weight, which we don't know yet. We have this distance was 2 meters. It was 1.5 plus 0.5. And then this distance is 1.5 meters. Okay, we don't know this weight. We don't know where it acts. Well, we know it acts at the centroid of that quarter circle. And we can look up the formula of where that centroid is, and we get that distance is 4r divided by 3 pi. So 4 multiplied by 3 meters divided by 3 pi. That works out to 1.27 meters. Now let's calculate what the weight is. The weight is mass multiplied by gravity. Mass is the density multiplied by volume. So we have 1,000 kilograms per meter cubed. Our density is going to be that quarter circle area multiplied by the 4 meter width. And then we have gravity. So our weight works out to 277.4 kilonewtons. So let's put that on the diagram here. Okay, now we have everything we need to calculate that that spring force. Hang on, that should be Fs. So we can find that spring force by summing up the moments about point A, and the sum of those moments are equal to 0. Let's put in a sign convention so counterclockwise is positive. And let's just start summing up all those moments about A. So let's start with Fx. Fx, we have a distance from 2 meters from A. We have Fy is 1.5 meters from A. Now the weight acts in the clockwise direction, so we have a minus force multiplied by distance. The Fs we don't know, but we know it's 3 meters away. Okay, so we have an equation here with one unknown in it. We can simplify and solve this, and we get the force from the spring is 177 kilonewtons. And there's our answer there. Thank you.